Welcome to Circuit Lab, practice number 14, PN Junctions. My name is Mr. Burleson, and you can reach me at geaux15@hotmail.com. We talked about diodes before and how it's a two-terminal electronic device that allows current to be conducted in one direction normally. Okay? We talked about how an ideal diode has zero forward bias resistance and it also has infinite reverse bias resistance. And we also talked about how you can figure out the forward bias voltage depending upon what type of material the diode is made of. We talked about ways to draw the current versus voltage curves for an ideal diode, and then how to approximate a real diode by either putting in a forward biased resistor and or the forward bias resistance, which is usually going to be very, very small. Keep in mind, most of the problems are for a silicon diode. So if you are going to put in the forward bias voltage, it'll be 0.7 volts. But let's talk about the linear approximation to a non-ideal diode. Okay, so for when your voltage is more than the turn on voltage or the forward bias voltage, okay, it has a small on resistance, very, very small. So that curve is going very steeply straight up. You're talking on the order of less than an ohm or a few ohms, okay? Now, if it is less than that forward bias voltage, but greater than zero, it's off with very, very low current. So it's almost negligible current, and that the point at which it's considered to go from off to on is sometimes referred to as an E. Now, if it goes zero, or it goes less than zero, the voltage, but below the Zener or avalanche reverse bias voltage, it's very, very negative with very little leakage current. It's referred to as leakage current because you're going backwards. So it's less than zero. And so now you're talking very, very small amounts of current. You're talking like microamps or picoamps, okay? Now, at some point, the reverse voltage becomes so great, you have something that's referred to as Zener avalanche. And then at that point, it actually acts as a short going the other direction with a very small off resistance. Now, remember we talked about light emitting diodes and how depending on the different types of materials that you have, they will emit different lights when turned on. But let's talk about what forms a PN junction. Okay, now a PN junction is a boundary or interface between two types of semiconductor materials, a p-type and an n-type. Okay, and so what you do is you take a normal semiconductor, like let's say silicon, okay, and then what you would do is that you will dope either positive sides, which you would dope that with excess holes, which are free positive charges in the outer shells of the doped electrons. So in other words, you get a positive ion and you inject that in part of the semiconductor. And then you'll put negative side. On the negative side, you'll have an excess of electrons. So in other words, these are negative electrons. This allows the electrical current to pass through the junction usually only in one direction, in the forward bias direction. Okay, now the diagram of what the PN junction looks like is shown to the upper right, where you'll see on the left hand side, okay, you have the neutral N region and the neutral P region. Okay, now what you'll notice is that wherever you have positive charges, these are ions that have fewer electrons than they need. So what ends up happening is that they become donors. And then what you'll see is on the negative side, you will have what we will call acceptors. So, how do you do that? So, you take a normal neutral silicon semiconductor, as shown on the left-hand side, and if I want to dope it to be with an N material, I will actually inject antimony, okay? And it creates an N-type silicon semiconductor, okay? So this definitely changes the properties of my semiconductor, okay? And what you see is that when I inject the antimony, which is shown by SB in the diagram, in the valence band, okay, I now have excess electrons. Now, I can also make the great part about silicon and other semiconductors is I can also do it the other way, and I can dope it with a p-type of silicon semiconductor. I can make it into a p-type one by doping it with something like boron. Now, boron actually has one less electron than silicon, and so what ends up is I'm actually basically adding in extra holes. So what you do is that here's a way of showing the difference of the N-type and the P-type. Donors are going to be positive charges for the N-type semiconductor. There are a large number of free electrons. There's a very small number of holes. Okay, so what that means is that you have positively charged donors, okay, and negatively charged free electrons. The supply of energy gives these negatively charged atoms free electrons and positively charged holes. However, if I make a p-type semiconductor, the acceptors are negatively charged. Okay, so there's a large number of holes, a small number of free electrons in relation to number of small number of free electrons in relation to the number of free electrons. So there are negatively charged acceptors and positively charged holes. Okay, so what ends up happening here is that the supply of energy gives me positively charged holes and negatively charged free electrons. So, what do we use for doping? Okay, so keep in mind that most single semiconductors come from group 14 of the periodic table. So, silicon, germanium, carbon. P-type doping usually comes from group 13, one less. Okay, and N-type doping usually comes from group 15, one extra. Now, notice how gallium arsenide is a semiconductor as well. And what you've done here is you've taken a 13 gallium and you've taken a 15 group arsenic, you've put them together, and so they actually act like they were in group 14. Okay, so that's why gallium arsenide has got a lot of really cool capabilities, like it's got faster switching, uses less power, etc. It is much more difficult, much more expensive to deal with, and it also has some issues with environmental impacts, arsenic. So when we put these N-type and P-type together, okay, as shown below in the diagram, you can see how we make the anode and cathode by putting a p-type and an n-type together. Okay, the positive side contains an excess of holes. Okay, the inside, the negative side, contains an excess of electrons. So what that does is that causes a situation where after we have overcome the initial charge issues by getting past the forward bias voltage, the electrons flow freely through there. However, that barrier becomes even larger if we reverse the voltage. So when we look at the I-V characteristics, and this one is a much more in-depth view of the I-V characteristics, okay, you'll notice that we have the forward bias. Above that, we have a very small on resistance. Now keep in mind the forward bias voltage is going to be like 0.3 volts for germanium and about 0.7 volts for silicon. Okay. Now, and then you'll notice that below that knee, if you will, okay, it's pretty much off. And then we get into the off, as we get below zero, we have a small amount of leakage current. Okay, but then we'll hit a point at a reverse breakdown voltage, and you'll see a Zener breakdown or avalanche region. Okay, now keep in mind that this drawing is not necessarily to scale, but it does show that the Zener breakdown or off resistance is actually even smaller than the on resistance. The on resistance is small. The breakdown in the reverse is virtually nil. So guess what? They actually designed some diodes to only operate in that area. Okay, so what it does, it actually makes for a faster switch with less resistance, and these are called Zener diodes. Okay, so if I don't put any type of voltage, okay, with zero voltage, it has a built-in potential, and the diode is considered off. The area between the N and P regions is called the depletion area. Okay. When the depletion area is large, no current can flow. That's why you need a forward bias voltage to reduce the depletion area to the point where there is no depletion area, and then the flow runs easily. When you get into the reverse bias region, okay, so we're less than zero, the diode is off. The depletion area keeps getting wider and wider and wider and wider. Okay. Eventually, it will become so wide that the depletion area becomes basically an entire conductor. And that's where we get into reverse breakdown or the Zener region. Okay? Most of the time, we're worried about the forward bias PN junction characteristics. Okay? Because that's when the diode is considered on. Okay, and this is how most diodes are designed to work. So in other words, after we get above 0.7 or 0.3 or whatever the forward bias voltage is, it pretty much acts like a small resistor, if you will, but the voltage is large enough to have reduced the depletion area, so it's small enough such that current can now flow. In the reverse area, okay, at this point, we have broken down the entire PN junction, okay, and we are now in the Zener breakdown region, okay, and at that point, we can actually we have even lower current, and you'll notice that the difference in the drawing for a Zener diode is that instead of just a flat line in front of the triangle, it makes like a little Z. So I'd like everybody to update their binder to get a competition record. I want you to design a circuit using an ideal diode, but I want you to include the forward bias voltage of 0.7 volts. So there's no resistance, but there still is forward bias voltage. Okay, and what I want it to do is that I want the output voltage will be the input voltage when above 3 volts and near zero when below 3 volts. Okay, assume generally ideal components. Okay, I would like for everybody to research semiconductor band diagrams and how they bend. Okay, so as you change the voltage, the band diagrams are going to bend. Okay, and I want you to show me how they work in zero bias, forward bias, reverse bias, and reverse breakdown. Update your binders with listing of common diodes and their properties, including Zener diodes. So you'll notice that all of this stuff is to add into your binder. Thank you so much.